and bases. Bronsted-Lowry acids and bases transfer protons back and forth, whereas oxidizing and reducing agents are transferring electrons back and forth. The weaker the acid, the stronger its conjugate base, whereas if we're talking about oxidizing and reducing agents, the stronger a reducing agent, meaning the further to the right and down on that SRP table, the weaker its complementary oxidizing agent, which would be on the left-hand side, just directly to the left of it, okay? So if we have a species that has a really strong tendency to give an electron away, then that means it's a very strong reducing agent. It is further to the right and down on the SRP table. Then it's going to have a very weak tendency to take it back. Okay? So if you turn the page, we're going to label some species on the SRP table. Some of them act as both reducing agents and oxidizing agents, and then some of their strength corresponds to electronegativity values. So I'm going to drag over this table, and then let's turn to the next page here. So I'm looking here, okay? So a lot of your transition metals that have varying charges can serve as oxidizing or reducing agents. And then the halogens on the SRP table are going to be arranged in order of increasing electronegativity. So here they've put the halogens in boxes for you, and then I'll go back and show you where these are on the SRP table. But you'll notice that iodine, bromine, chlorine, and fluorine are in order of electronegativity, because if you look at their group on the periodic table, you've got F at the top, and then you've got iodine down at the bottom. Fluorine would be the most electronegative. Iodine would be the least electronegative. So as I go up the SRP table, my electronegativity is increasing for those halogens. So that means an increase in electronegativity means an increasing in their oxidizing agent strength. So fluorine would be the strongest oxidizing agent, whereas iodine would be the weakest oxidizing agent out of the halogens. So if we're trying to look at this on the SRP table itself, so you'll notice you've got fluorine here at the very top. Chlorine is here underneath it. Bromine is here. And then your iodine is down here. Okay, so these are the halogens that I just labeled for you. And then your electronegativity increases in this direction, which is the same direction as an increase in the oxidizing agent strength. Okay. Now, the strength of an oxidizing agent is called its reduction potential. So I'm going to label this in a different color. The reduction potential is abbreviated a capital E with a little degree symbol on it. And if you look here, these are your reduction potential values here on the right side of the SRP table, okay? Reduction potential is the potential to be reduced. Okay. And oxidizing agents get reduced, therefore they have a reduction potential. And this is measured in volts. So you're going to see this with a capital V as the unit after it. Okay, so these are all in volts. And F2 being the strongest, bless you, F2 being the strongest oxidizing agent here has a reduction potential of positive 2.87 volts, okay? Something else that I want to point out to you on this SRP table is we have some of the 8 ions like bromate, permanganate, chlorate, dichromate. They're in the top left of the SRP table, which means they're strong oxidizing agents. So if I want to label them, I'm going to put this in a different color. You'll notice you have permanganate here, you have bromate here, iodate here, nitrate here. So the 8s tend to be really strong oxidizing agents. Okay, so permanganate, bromate, iodate. God bless you. We've also got dichromate and chlorate. Dichromate is right here. Can you guys see those okay? Do you want me to repeat what they are? So permanganate, MnO4, bromate, BrO3, dichromate, Cr2O7, IO3, iodate, and then NO3, nitrate. Okay. Okay. So oxidizing potentials measure the strength of reducing agents, since reducing agents become oxidized when they give up electrons. And when the reduction half reactions, so these are half reactions here. And if I read them backwards, meaning I read them from right to left, then they are oxidation half reactions. So we should probably make a note down here that half reactions read right to left are oxidation. Half reactions. Okay? So that means that whatever the reduction potential is, it would be the opposite sign. So for instance, this down here would be negative 0.34. Okay? I can also use aluminum as an example. Aluminum, I don't think it's shown here. I'd have to like scroll all the way down. But you'll notice that Al plus 3, which is down towards the bottom, has a reduction potential of negative 1.66 volts. But if I read that half reaction in the opposite direction, the oxidation potential is 1.66 volts. So if I'm looking at this mercury 2 reduction potential, it's positive 0.85, but if I read it in the reverse direction, I'm looking at its oxidation half reaction, this would be a negative 0.85 volts. Easy enough? Okay, let's take a look at the quick check. Everything that I just said is outlined here within this reading down here, okay? So let's go over here to this quick check. And with the person sitting next to you, I'm going to have you read through questions 1 through 7, and let's see what you come up with. It's AL.
Oh wait, no, that's the weaker. Forgot it goes in the opposite direction. elements of Fe is listed.
Oh yeah, it's right here.
Okay. What was that? Fe plus 2 or Fe plus 3?
It's above I don't think that's okay. Which is a greater oxidation potential?
So it's a stronger reducing agent. So I think it's I. A greater reduction potential, so it's on the left side.
It could be L. Yeah, because we are.
I found CR plus 3. SN strong.
Which is a greater reduction.
And the hypothetical elements A2 plus a stronger oxidizing agent than B. What is greater oxidation potential, A or B? If it's a stronger oxidizing agent, that means it has higher reduction potential, which means it has lower oxidation. What is the reduction potential of AG? 0.8. What's the That's the reduction, but the oxidation is positive.
I found it as
Right? So you do, because that's what's the stuff there's a reduction. So then you have to flip the signs.
Does it help if I give you those notes?
Yeah.
That's like last time, but either way it's greater. Yeah. So I think the SRP table can be very, very confusing to understand, but I feel like if you have all the little notes, it makes it a lot easier. So the stronger reducing agent would be the one that's further to the right and down. Agreed? On the SRP table. So I got SR. Did everybody get that?
Yes.
And then for number 2, the stronger oxidizing agent would be on the left side, and for this to the top, so that would be Fe plus 3. Yeah? Number 3, which one has the greater oxidation potential? So when you're looking at oxidation potential, aren't you reading those half reactions from right to left, and then you're flipping the sign? So here I got I negative 1, and then the reduction potential, which is red left to right, like the half reaction stays as it is, that would be Sn plus 2. Questions for me so far? Okay. A and B were hypothetical elements. A plus 2 was a stronger oxidizing agent than B. That means that A plus 2 would be further up on the left-hand side. Which has the greater oxidation potential, A or B negative? It would be B negative because it would theoretically be on the right side, down a little on the right. Number 6, the reduction potential for Ag plus is positive 0.80 volts because you read reduction potential from left to right. And then the oxidation potential of calcium would be read from right to left, so that would be a positive 2.87 volts. Okay, so could you do this without me? If I were to give this to you on a quiz, like questions just like this.
Yeah.
On Canvas, and you have the SRP table. Okay, we only have one more thing to do and then we're done. Okay, so we're going to take a look at determining the predominant redox reaction. We're actually not going to do the redox titration section. So the very last little section, you can cross that out. No redox titrations. I know you get great joy crossing things out in the book. Okay. All right. So determining the predominant redox reaction. So the predominant redox reaction is going to be between the chemicals in a mixture, the one that is the strongest oxidizing agent, so the one that's the furthest to the left at the top, and the one that's the strongest reducing agent, so the one that's furthest to the right and the bottom. I'm trying to get this to refocus. It's being very temperamental. My video camera, it's just like, it's aging, I think. It needs glasses. It's not focusing at all. This is terrible. Let's see if I can fix this. Okay, so let me take this out of the picture for a second. Just might work. Okay, let's go to the next page. Let's go straight to the practice problems, and we're going to end on that. Let's see if I can get it to refocus. It's so funny how it does that. Now it's focused. Okay, write the predominant redox reaction that will occur in each of the following mixtures. Okay, so if we look at number 1, we want to look at what you're given. You want to find out which one of these substances is furthest to the left and the top on the SRP table, and which one of these substances is the furthest to the right and down. Okay, so if we do that, you'll notice that SN plus 4 is high on the left. So this one is on the left and the top. Okay, whereas nickel is going to be on the right and down. So since those are the two that are furthest apart, this would be the reaction that takes place. We're going to use their half reactions to write the overall redox reaction that occurs. So we're going to take our SN plus 4 plus 2 electrons, which goes to SN plus 2, and then your nickel is going to give its electrons to tin. So we have these two half reactions. And then since the number of electrons matches in each half reaction, then I can cancel the electrons. And this is the overall process that you're left with. Does this make sense? Okay. Okay. Let's take a look at number 2. For number 2, I have aluminum by itself. This is a metal, which means it may switch places with the metal in the compound. So this is copper plus 2. So this is a metal replacement. So if you look at the SRP table, you're looking for aluminum solid, where it's located, and you're looking for Cu plus 2. You'll notice the aluminum solid is at the bottom on the right-hand side. So since this is on the right-hand side at the bottom, that means it's going to give its electrons to copper. So this being a single replacement reaction would be CuBr2 plus aluminum solid. Aluminum will combine with bromine, you'll get AlBr3, and then you'll kick out copper metal. And then in order to balance it, you need a 3 in front of CuBr2, a 2 in front of Al, a 2 in front of AlBr3, and then a 3 in front of copper. Now, we have to break down anything that is dissolved in water. So we would break down these two compounds. So this is 3Cu plus 2, and then 6Br, negative 1. and then you tell me what's gonna cancel.
The 6Br minus 1.
Yeah, the 6Br negative 1, these are your spectator ions because they're the same on both sides. So those would cancel, and then what you're left with is the overall reaction that would occur. Okay? We're
Do
done.
we include solids?
Don't break down solids.
Okay. Well, like, if we, like, finish, would we write just 3Cu plus 2 goes to 2Al?
Here. Whenever you kick out a metal, and it's going to be by itself, it's just going to be solid. It won't be an ion.
So it's, like, not included in the equation? Okay.
Okay? We're good? All right, that's it for this section.